Okay, so those are Newton's laws. So from Newton's laws, what kinds of things have we discovered? Well, our goal was to try to figure out exactly what we mean by mass, velocity, momentum, and energy, and we've discovered two of those. According to Newton's law, mass is a scalar, which means it's just a number. It has units with it associated with it, but it's just a number. It measures the tendency of a body to resist acceleration. That's what the mass does. So you got an arrow in motion. The heavier the arrow is, the more it's going to resist being stopped. The more it wants to keep moving the way it's moving. A lot of people assign this definition to momentum. They say the momentum is the tendency of a body to stay in a particular state of motion. That's wrong. That's what mass is. Mass is the tendency of a body to resist acceleration. The more mass there is, the less acceleration there is for a given amount of force. So don't confuse this with momentum. It is not momentum. Velocity, on the other hand, is a vector quantity, and it specifies the state of motion of a system at a given time t. And really, that's all it does. It just tells you, it's a way of saying this is how the thing is moving, and that's it. It doesn't. There was nothing in anything that we looked at that let velocity tell us anything about anything. If I tell you the velocity of something has a magnitude of 35 feet per second, that alone tells you nothing other than that's how fast it's going. And as long as if I'm giving you an actual velocity, then I'm also telling you what direction that travel is happening in, and that's what velocity does. So we have two more quantities, momentum and energy, that we need to define. So let's go ahead and define those as well. So with momentum, first of all, the symbol that we give momentum is p, and we're going to see that the momentum is in fact a vector. So actually, I'm gonna erase this because I want to go through this stuff a little bit. I don't want it all being looked at one time because it will get to be confusing. So let's kind of dig through this and see what this says. So let's take a collection of bodies or systems. So here's a whole bunch of different particles in a box. Okay, and these particles are moving around and they're bouncing off of each other, so they're exerting forces on each other. So let's take the ith particle. Let's just name this particle I, and try to figure out all the forces that are acting on this particle. Well, it could be feeling a force from any of these other particles. So perhaps there's a force that it feels from this particle, and that force is pushing it this way. Perhaps there's a force it feels from this particle, and that force is pushing it this way. Perhaps there's a force from this one, and it's pushing it this way. Maybe it doesn't actually feel anything from these two particles. Maybe there's no forces exerted on them there. And so the total force acting on this particle, well, force is a vector. So what do we do if we want to get the total force? We take and add up all of the forces from all the particles acting on it. So if we add all the forces together as vectors, that gives us the overall force acting on this ith particle. So that's what we're saying here. Sum, this just means add up from J not equal to L. All right, that's a little bit confusing. What does this mean? We're looking from the force from the jth particle on the ith particle. So say this particle is 2 and this particle is 1. We're interested on particle 1 on 2, particle 3 on 2, particle 4 on 2, particle 5 on 2, and particle 6 on 2. But we're not interested in particle 2 on 2 because an object can't exert a force on itself. So so when we say J not equal to I, this just eliminates the possibility of having 1, 1, or 2, 2, or 3, 3. This is looking at all possible combinations for the ith particle. And note from Newton's second law, then that force must be equal to the mass of that particle times its acceleration. Okay, so we've determined the force, and we're saying now we can figure out the acceleration of that particle now that we have that force. Okay, we've determined the force by adding up all the other forces from all the other particles acting on it. All right, now what is the total force then? What is the total force acting on the whole system of particles? The total force acting on the whole system of particles, what's that going to be? Well, that's going to be the sum of all the sum over I of all the particles forces acting on themselves. So I'll write this down and we'll see what it actually tells us. All right, so what does this thing say? Well, this thing says, okay, we take all of these forces. Notice I've just rewritten this part here, which is just this. So this piece here is just F sub I. We're going to take all of those and just add all of those up. So once I know the net force acting on each particle, so we come over here and we erase these individual forces, but I know this particle has a force acting on it this way, and this particle has a force acting on it this way, and this particle has a net force acting on it this way, and so forth and so on. These are also all vectors, and we add all of those together, and that will give us the total force acting on the entire system. Now, we're going to assume this system is isolated. That is, that the total force acting on it is zero. There's nothing outside of here acting on these particles. So what does that mean? That means when we add up all of these little force vectors of the particles acting on each other, we have to get zero. So by definition, we end up with zero in this moment. All right, so now we're going to take off with a little bit of calculus. So let's take this total force, which is a vector. I need to put here this total force is a vector, and it's zero. That's going to be equal to the sum over I. Now, this is just the mass of the ith particle times the acceleration of the ith particle. This is also a vector, and this is also a vector. But what is that? So here's where knowing our definitions is helpful. We're going to add up all of the forces acting on all of the different particles, the net forces acting on all the different particles, and that will give us the acceleration of those particles, which is the change in velocity divided by the change in time, the derivative of velocity with respect to time. Remember, that's just a different way of writing down the vector A. So this is the acceleration of the ith particle. Now, one of the rules for taking derivatives, and you'll have to take some calculus if you want to do this, if you want to learn this, is that when you have a function multiplied by a number, you can take that constant, as long as it's a constant and mass is a constant, in and out of the derivative. So in other words, I can take this mass and plug it in, move it from outside of this derivative to inside of the derivative. So the mass of the ith particle times the rate of change of the velocity of the ith particle is the same thing as the rate of change of the mass times the velocity of the ith particle. They give the same answer. And then furthermore, there's something called a sum rule for derivatives. And so we can also take the derivative outside of the sum here. That is to say that the sum of the derivative of a bunch of objects is the same thing as the derivative of the sum of a bunch of objects. In other words, I can take and bring the sum in here as well. And so I can rewrite that this total force, what is this total force? It's going to be the derivative with respect to time, the rate of change with respect to time of the sum of the mass of the ith particle times the velocity of the ith particle. And that, we said, has to be zero. So notice what this says. It says that if I take and add up the mass times the velocity of all of the different particles, the rate of change of that total will be zero as long as there's no force acting on my whole system. Okay, what this says is that the sum of the mass of the ith particle times the velocity of the ith particle for all I particles is equal to some constant number. In this case, a constant vector. Okay, and so that's interesting. So what we're going to do is we're going to define this quantity. First of all, what kind of quantity is this? It's a scalar, that's a mass, and times a vector. Velocity is a vector. And so whatever this thing is, it's also a vector. And we're going to call this the momentum. More specifically, the linear momentum, but we're going to define this. We're going to make this definition. If you don't know, a triple equal signs means definition. So we have a definition here that the linear momentum is the mass times the velocity of a particle. And what this says is if we take the momentum of the first particle and we add to it the momentum of the second particle and we add to it the momentum of the third particle, so forth and so on, as many particles or as many bodies as we have in our system, all the way up to the nth body, however many we have, we add those together and that will give a total momentum for the whole thing, because these are all vectors. We can add the vectors and get an overall vector. and that as long as there's no forces acting on externally on our system, that total vector will be constant. It will never change. This is what we mean when we say momentum is conserved. If you take these quantities and add them together, their sum will be constant. Notice they are not constant. Their sum will be constant, assuming if no external force. This is extremely important. People forget this. They just say, well, momentum is conserved, and they stick at that. No. Momentum is conserved when there's no external force acting on a system.